Manager in oil and gas company Kalman in Houston, USA, and it is my pleasure to do this presentation for the 10th Congress of Process Engineers in Peru, in Lima. The title of my presentation is Data Assimilation and Artificial Intelligence for Process Automation. A couple of words about myself. So I graduated with my master's and PhD in applied mathematics and fluid dynamics from Moscow University, here on the right. I worked in Europe several years, in Switzerland, Germany, and then I came to the United States to work for Yale University, where I was a research scientist and taught classes at Yale Engineering School. And then I started working for the industry. I worked for Corning Incorporated and Halliburton. And now I'm a research and development manager at Corva, which is a very intensely developing company in Houston in the domain of oil and gas. We are using artificial intelligence and machine learning for real-time applications like drilling and completions. We are also using deep neural networks, Gaussian process regression, and data assimilation techniques, and I will talk about this in the presentation in the following slides. So first of all, what is artificial intelligence? Artificial intelligence has many definitions, but in general it is science connected with algorithms that normally require human intelligence. The machine learning is a part of artificial intelligence, which is dealing with algorithms that learn from data. So when we talk about artificial intelligence, machine learning is always a part of it. So there are very little artificial intelligence applications without machine learning these days. So there are different parts of artificial intelligence, but first of all, there are artificial narrow intelligence. This is a big part which is already there in the world. This is about machine doing specified tasks. For example, our driverless cars, warehouse robots, and semi-autonomous weapons. These are all applications which are already there in the fields, on the roads, in the power plants, in the production plants. However, there are future applications that include extension of the human senses. This is particularly important for a direct brain-to-computer connection. So if you have a specific software and hardware like microchips, and then you can organize cortical interface and connect your brain directly to computer, avoiding the keyboards and just using your thoughts to control the computer. This because you can also connect a multiple set of devices to the interface. You can receive, transmit radio waves, Wi-Fi, and other applications directly to the brain, which means practically we can reach technical telepathy and connect to internet or with each other directly using radio waves and electromagnetic waves. So on the right you see the diagram which shows the brain and interface, and then you can connect all of the possible devices. And this is particularly important for people that have disabilities, like who are blind or deaf or paralyzed. This will allow them to go back to the normal life and start seeing, hearing, and moving as good as before. The picture that you see on the right now, this is, for example, a picture of the subway, and you see that everybody's having the iPhone or other smartphones. So because people are so used to the interfaces like smartphones to connect the internet to each other, to call and to get information. But maybe 20, 30 years from now, you will have a very different picture. Practically, you will not see any devices at all because everything is hidden inside your brain. You have microchips, and you can connect to each other. You can connect to internet just by thinking about it. So that is, and it is very, very real situation. So there are millions of dollars that are spent each year for this research, and there are initial research results already positively indicating that this will be soon enough. Artificial general intelligence is a little bit more complex thing. So this is about the capacity to understand and learn intellectual tasks that a human being can. So if you create a robot that has artificial general intelligence, it is very difficult. It will be very difficult to see the difference between the robot and the human unless you see the object directly. So in 1950s, a brilliant scientist whose name was Turing invented the test to show when we can reach this artificial general intelligence level. So, for example, when we have a computer or robot that is already like well developed, and we can put it in one room, and human responder, human being in another room, and the interrogator can connect with robot and with another human through the text. And when the interrogator doesn't see the difference of levels of answers between computer and the human, so then we will reach this artificial general intelligence level. So that is a simple test, but since then there have been many tests developed, but this is just to give you some idea about how artificial intelligence important is and what is the level of AGI. So where is it possible to do? Once it is possible to do, then the humans will be replaceable by computers and by robots. And for that purpose, they need to learn how to reason, plan, and learn, and communicate in other languages, and particularly natural language like English, and integrate skills for a common goal. That means that they can organize societies, teams to work on a specific problem or specific application. This has been described many times in the science fiction, starting from probably Space Odyssey, 2001 Space Odyssey. You have this Health 9000 computer, and a number of recent movies, including iRobot. It's interesting that in all these cases, the robots decided that humans are not necessary for their development, for their well-being. So they tried to get rid of the humans. In the case of HAL, so he tried to kill the whole crew of the spaceship, and only one astronaut survived by miracle. So miracle chance. So that is one of the situations when the robots was not programmed to destroy the spaceship or to kill the crew. It decided that it makes sense for the robot to survive, to have better chances of survival if the humans are not functioning. So this is a kind of example when the robot shows artificial intelligence, but it can be destructive too. The machine learning is part of this artificial intelligence. So once we want to develop a robot who mimics the thinking of the human, of course it has to learn, and learning, as I mentioned, is a significant part of AI. So what do we have at this moment? We have several different types of machine learning already developed and already used extensively. For example, supervised learning and is used in driverless cars and other applications I will talk about. Unsupervised learning is classification of results. For example, if you have information about the customers of Netflix or Google, that is how the customers are split into groups. For example, if you have information about the Netflix users, you can see the clusters will represent different interests of the customers. For example, the ones that like the action movies from another set of customers that like the romance, and so this is very useful and very practical applications. Reinforcement learning is another quickly developing part of machine learning, and these are algorithms that can play games. The computers can play games already much better than humans in several different games, like in chess or in Go. But in some games that require interaction between humans, for example, or computers, the humans are still better than the computers, and that is where the artificial general intelligence is needed. So that is where this direction. That is the direction of the future development. And finally, data assimilation. It is a very practical machine learning set of algorithms, and it is used, for example, when we have a lot of information coming, and that is used to adjust, fine-tune the mathematical models, like the models that are used for weather forecasts and hurricane forecasts in the atmospheric science. I will start with supervised learning, and I will briefly talk about other types of learning. The supervised learning is a very wide, has a very wide range of applications. I want just to give you a general sense of it. For example, suppose you are a realtor and you have information about all houses that are being sold in this city, and this information, of course, includes the size in meters squared, the number of bedrooms, the number of floors, and the age of homes. And based on that, also the information about the price in thousands of dollars. So if you have many thousands of these lines, it can produce what is called training set. So you can train your neural network based on this comparison between input, which will be 4 columns on the left, and output, that is the price column on the right. And you can build a model using neural networks of Gaussian process regression. And this mathematical model is practically a set of coefficients, but this will allow you to calculate the price of the future real estate. For example, if I train the model, I can give the size of the next house. I have no idea about its price, but if I know the size, number of bedrooms, number of floors, and age of home and years, the model will tell me how much I can expect it to be worth in the market. So that is widely used. Other applications, there are other popular applications. For example, speech recognition that already used in computers like Siri, and the image recognition, which is widely used for many years already during the post service. So if you write your address, the envelope goes through the special machine, and it uses the artificial intelligence supervised learning, which is based on a database of many hundreds of thousands of examples of handwriting, and comparing your handwriting with this database and the specific algorithm, it can tell what exactly you wrote on your envelope as an address, and that is how all of the millions of letters go through the United States Post Service, and each of these letters is read by computer, and each of this situation is dealt with using supervised learning. Email spam detection. So this is how many companies they detect spam, and you don't need to see all of the emails that come to your email address, because most of them are filtered, and you don't see a lot, maybe 1 or 2 instead of hundreds. The handwriting recognition, as I already said. The following example shows the unsupervised learning. Suppose, just one example, suppose you work for a company and you're in the financial part of it, and you have information about salary of the personnel and age, and each point of this is an employee, is a person, and you can see that they all have different age and different salary, and suppose these numbers are just normalized values of their salary and of their age, so normalized. And you want to make analysis of this information. So you say, I want to have to split it into 3 clusters, 3 groups, and let us see how the computer will split. So the picture on the right shows these 3 clusters: the green, blue, and red. So if you start looking at each of the points, you will realize that, for example, the highest salary and higher age is probably the managers, technical and administrative managers. They more experienced and they have higher paycheck. The technicians, they may have comparable experience, but they don't have this qualification, so their paycheck is lower. The blue points represent people who are younger, but more qualified, better educated. So their salary can vary from very low to very high. Why we need to do this in our industry, for example? Why do we need automation already now? How we can use it? The problem with oil and gas that we now face the need for automation, which means that we need to make operations running automatically without interference of humans or without human supervision, constant supervision. Maybe there will be occasional supervision. But for example, this platform, this rig on the left has no personnel. So it is designed to work autonomously without human being. And there are robots there on this rig, and they do everyday perform tasks that normally are done by humans. And once in 2 weeks or more than that, the human crew comes over and just tests, checks if everything is running well, and there are no other malfunctions that are not possible to identify from a distance. But normally nobody works there, as no human beings is needed for that. But this is just a few examples. In the future, everything will work like that. So all of the production plants, all of the rigs in oil and gas industry. So practically the cars will be driverless. So this will come just in a few decades, 1-2 decades from now. Very, very little time from now we will have this. But we need to solve a number of problems related to this. So these problems from the mathematical modeling viewpoint, there are two of them. One is the speed, and second is account for the sensor data. When we talk about speed, it's a speed of doing simulations that are necessary for these processes. We need to do simulations modeling the processes here for controlling the parameters of this rig, of the operations. If you don't know how it will behave, and this is described by mathematical models, we can't do control in real time. So we need an operator, so a human operator. So these models must be very, very fast. So they're called proxy models or simple models or reduced order models. That is the set of models that can work in real time very, very fast in just seconds. So we need to develop them. Another requirement that these models, these representative models, need to be to connect to the sensors. The sensors are detectors that can measure parameters like properties of the fluids, temperature, pressures, or positions of the mechanical devices. So this is number of operations which require this, electrical currents, rotations of the rotating equipment. Everything can be measured. So, but how to connect this to the models that we use for these processes and for controls? So the data assimilation is exactly that sets of algorithms that connect the mathematical model for the process with the real-time sensor data. So there are a number of algorithms that can be used, but the most efficient ones are ENSEMBLE, Kalman filters, and Markov chain Monte Carlo. I will talk more about the ENSEMBLE Kalman filters. That is the most flexible algorithms which is used in the industry, and it is being quickly developing and applied to many other applications in different industry. This is the diagram showing how it works. Suppose you have a model of the process, like a flow in the pipeline, and you can do predictions. If you change parameters, you can do predictions what will happen with the flow rate and the pressures, and then you can compare these parameters with the field sensor data for pressure meters and for flow rates, and the data assimilation model. This does this comparison and gives you recommendations how you need to modify parameters of your model so that it will represent the pipeline, for example. And this model inputs, they will be corrected and they will be put back into model, and this will allow the model to be always representative and adjusted to the real-time situation. for example, if it is the situation with the pipeline, then the properties of the oil or properties of the gas, they change with temperature, and the temperature, of course, changes very, very rapidly sometimes when the weather changes. So you need to account for these changes, and in real time, very fast, to change the parameters of the pumps and parameters of the whole system. And that is where the DA model will help you. So from the measurements of temperature, it will tell you how you need to change the settings of the pipeline. So this is mostly done by ENSEMBLE Kalman filter. The Kalman filters are very, very popular in the control theory. It's a significant part of the control theory. So there are many scientists that introduced that worked in the area of controls of the random processes, and Norbert Wiener did a lot, Kolmogorov, brilliant Russian scientist, and Stratanovich, and Rudolf Kalman himself. So the guy is very, very popular in the US, and here he's shown with the Congressional Medal of Science, so that is the highest scientific award that can be obtained here in the US. Kalman, when in 1960s, he was a young guy, and he developed this brilliant algorithm for the filtering and prediction problems, for practical problems, which many of them are being used now in the navigation devices, in the tracking systems. The algorithm has only two parts, that is the predictor and corrector. So the predictor just uses mathematical model to predict the position, the system in the following moment of time. So if you have an aircraft, there is a model of the aircraft which will tell you where it will be located in, say, in 10 seconds or in 1 minute. The corrector is using the data, which is dt here, the data vector from the measurements that the navigation system and the measurement tools, detectors, sensors provide. So if your position, if the system parameters are different from the predictions, then this bracket on the right is not zero, and you can correct your parameters. That is the essence of the Kalman filter, and that is a very simple algorithm that can be used for different applications, but primarily for navigation and for tracking. Like in this Second World War aircraft, you can the fighter plane can track the position of the bomber plane, and using this algorithm, you can predict the location much better and use it for the targeting. This is another interpretation of the same that I just described. So suppose you have your mathematical model, and it predicts the position of the aircraft, like on the left, and it is this cloud here is the distribution of possible locations of the plane and its velocity. So it's a kind of Gaussian distribution, and in the middle of it, it's like the most probable position and velocity, but it is not very accurate, which was the case in the 1960s. But you can do measurements, and the measurements also provide you with accurate, not very accurate data. So you have a distribution like this RK, and this is also position and the velocity. And these readings are not accurately distributed. The actual position and measured velocity are not 100% accurate. But if you overlap, organize composition of these two distributions, like is shown on the right, the overlap of these two clouds has a much narrower distribution. It's another distribution, but which is much sharper, and the result is much more accurate. So that is the essence of the Kalman filter. It is a combination of your model and combination of the measurement. As a result, you have much better measurement predictions. So this increases the accuracy of your measurement significantly if you know how this mathematical model works. And this is why it is called filter, because in reality it's not filter, it's a combination of machine prediction, of mathematical prediction, and the measurements. So this is Kalman filter. It was immediately used in 1960s, and this big airplane, military airplane C-5A Galaxy was the first plane to use the navigation system based on the Kalman filter. And it's been used in commercial and military aviation since then. The other application also in 1960s was the Apollo mission, and the computer there on the Apollo had only 2 kilobytes of random access memory and 36 kilobytes of magnetic rope. It's like a very distant equivalent of the hard drive, but it is only 36 kilobytes. And still, with this very, very tiny memory and computer speed, the CPU speed, it was possible to use this algorithm because it was so simple. And it allowed the Apollo mission to be successful because this was a significant part of the inertial navigation system. So coming back to the mathematics, so what can we do with this Kalman filter besides the navigation? For example, take a situation when you have a robot which is one-dimensional. This one-dimensional robot can be any system that has one coordinate in time. So that is, for example, a bus that you take to drive to the school, or your car that drives along the same route every day. At every moment you have one location, and at each time you can say where your car is located. So on the left you see the equation describing the location, and this is the derivative of time over time is the velocity of the car, and r is the radius of the wheel, and omega is the angular velocity of the wheel that you can measure directly. You can't measure the distance in the car, but you can measure the velocity of the rotation, and the velocity in respect to the road cannot be normally measured unless you have a navigation system like GPS. So you can solve this equation, and if you don't know the radius, you can solve it like shown on the right. For different values of radius, you will have different predictions for the distance for different times. And if you don't know the radius, you can find it now if you compare what you predict with independent measurements of your location, like GPS system. Like shown on this right-hand side, at time equals to 3, you have the location, like 33 hours and 30 seconds. You can see how different these locations are. But one is very good, and that is gives you the radius of the wheel. This is not a very theoretical example, but this is exactly how the pressure measurement system works in your car these days. So they compare the distance, the rotation speeds of different wheels. And the one which is flat is a flat tire that has, of course, very, very low rotation speed. So this is very high rotation speed. This is not a very artificial example. But on the other hand, it shows how this Kalman filter can be used to identify its parameters of this model. You just need to run the trajectories many, many times and compare the predictions with what you measure. That is the essence of the ENSEMBLE Kalman filter. That is extension of the Kalman filter that was developed by Evensen in 1994. Here, Evensen is a Norwegian scientist who worked in the atmospheric science. And atmospheric science is a science where you have a number of models. Each of these models can be compared with measurements of the weather stations, like temperatures and pressures and the velocity of the wind. So this allows you to compare your model and make it constantly adjustable. For this purpose, Evensen developed the nonlinear Kalman filter, which has mathematically the same form, but the difference is that this state vector for this algorithm, it contains model parameters, like the parameters of the model that you use to predict the weather or to predict your process, and also measurement parameters. So this Kalman filter can filter both parameters of your model and the measurement data. So, and the algorithm itself also has this prediction part and corrections step. The GT, which is Kalman gain, needs to be calculated based on simulations that are run with different initial parameters. So for example, you can run this atmospheric model with different initial values or different coefficients for the model, and see how the results are changed, and then compare different predictions with what you measure in the weather stations. And this algorithm is very, very effective, and it can be used, it has been used in the atmospheric science first, then it came to the oil and gas field, and now is used in many different applications there, and I'm using this algorithm too. So how different data assimilations from supervised learning? They're both parts of the machine learning, but they're very, very different in some sense. The supervised learning, for example, is a universal algorithm, and you only need a training set. That means inputs and outputs, like in our example of the real estate, or you need to compare show the robot how the car driver drives the car. So that must be a training set, and that is it. So the mathematical model is inside this algorithm, so it can be it is developed by applying the neural networks, for example. And after that, it can be applied to any problem that has this training sets. It doesn't need any additional modeling. But data assimilation is a different thing. It is also a universal algorithm, but it needs a representative numerical model. For example, a model of the spacecraft or a car or an aircraft, and the model is a mathematical model that contains some parameters which you don't know or a priori, and that needs to be adjusted. And that is why it needs the measurement data. So it doesn't need just a training set, it needs constant measurement data, and it requires the mathematical model. In return, it is a very efficient algorithm, and it can be applied to problems of any kind if they can be modeled. So for example, in the Space Odyssey 2001, the HAL 9000, the robot, it knew both the supervised learning and data assimilation, because it has to control the position of the craft, of the spaceship, calculate the trajectories. So it had this data assimilation module, and of course it had the supervised learning and reinforcement learning, and it had this reasoning that allowed it to make very, very complex plans, like destroying the crew. So it had all of the intelligence, more than actually had superhuman intelligence, because it also had that mathematical skills that normally the humans don't have. But let us consider how these two algorithms work on the same problem. It is a very simple example where you have the flow of water in a pipe, and this is a long pipe, horizontal pipe. It has diameter, for example, 5 centimeters, and the length is 100 meters. And this is water conditions, water parameters. And you can measure pressure at the beginning, at the end, and you can measure the flow rate through this system. So if you apply the statistical models and statistical modeling and the supervised learning, principal component analysis, what they say, you will understand very fast that the flow rate is the function of the pressure drop. It is not the function of P1 or P2. It is the function of the difference between these pressures. Only the difference between pressures is important. If you know the pressure gradient, pressure differential, you can calculate the flow rate simply by looking at the table of these measurements. So you can use this table to train the neural network directly. On the other hand, if you know the fluid dynamics, you can understand that the pressure drop is the some coefficients times the flow rate to the power of alpha. And for laminar flows, it is 1. And for regular turbulent flows, it is close to 2. So it's this kind of parameters that you can adjust, and also the surface of the pipe is important. So all of these parameters can be slightly varied, but you know that it is between 1 and 2, and k is also can be evaluated. So you can apply both algorithms, and let us see what for this problem and find this function and use these models, resulting models for applications. So when we look at these predictions of this model of the data assimilation and neural networks, A and N, you see that within the training domain, suppose we train our model between 1 and 2 in the dimensionless parameters. So the predictions are very close to the exact solution, exact situation. And so you can use both. But the DA, data assimilation model, requires less points, but still they're both applicable. The situation is very different if you start looking outside the training domain. The artificial neural networks, they can be applied only within the domain. They can be used to predict the position, the property of the system outside the training domain. Whereas DA, the data assimilation, can do the prediction very well beyond the training domain if the model is correct. So you can train your DA model on the training set and then use it for predictions to much higher flow rates and much higher pressure differentials. So this is a significant difference between different kinds of machine learning. So supervised learning is good only if you are inside the training domain, and the data assimilation allows you to go well beyond the training domain and use the training set just to calibrate your model. So these are two different things. And this difference is the same quality with the same for very, very wide set of different applications. So this shows how these methods differ. I can give you a couple of examples how this can be used. This data assimilation can be used for different practical applications, more complex situations. For example, if you look at the fracture production, so we have a wellbore in the rock, and we organize fractures which are cracks in the rock, and they are almost parallel planes. And the gas and oil, they flow from the formation to the surfaces, to these cracks, and then through each crack they go inside the wellbore, the pipe, and then they can be delivered to the surface of the formation for the product. And it is production practically. So one can build a model of this reservoir model and see how the pressure inside the formation changes, because you open your well, the pressure is reduced, and the pressure inside the reservoir is very high. But when you connect the fractures to the pipe, the pressure inside the fractures is low, so the pressure inside the reservoir drops. And this is simulation show how it happens with time. So you can predict for different properties of the formation. You can predict how fast this happens, but these properties of formation you don't know in advance. That's the problem in oil and gas. So you don't know properties of the rock very accurately. So when you have a long well-bore pipe inside the formation, and you have a number of fractures, each fracture can be in different geological zone that have different permeabilities, and there is no way you can measure them directly. But you can measure pressures in the system close to the wellbore, and using the mathematical modeling and algorithm, data assimilation algorithm, you can, instead of measuring the permeabilities, you can just measure the pressures, and then using the model recalculate the pressures into the permeabilities. This is called soft measurement, and the algorithm of ensemble Kalman filter is very successful here. So we create the state vector as shown on the right. It contains permeabilities, which we need to determine, the pressures that we can measure, and the flow rate that we can measure. So we apply the algorithm developed by Evensen in KF, and already the first iteration, which is shown on the left, gives us a very good approximation to the true results. So we can measure the pressures, but determine the properties of the rock, like permeabilities, which is extremely important for future estimates and for understanding the formation. So this is one of the examples. Another example is also very practical. It is what is called midstream. We have a pipeline, and we always have some leaks. Sometimes they are small and negligible, but in many situations they can be serious if there is a damage of the pipeline, and due to weather or some accidents, And we can't measure the flow rates at every point, but we can measure pressures very well inside the pipeline. And this allows us to evaluate the leaks in each of the sections of the pipeline. The length of this pipeline can be many, many kilometers, and but we can split it on the sections, and whenever we measure the pressures, we can split the pipeline into different sections and use this algorithm. So the same thing, the state vector of the system will be measured pressures and flow rates that we need to determine. So for different flow rates, the simple formula gives us the distribution of pressures, but we can run these predictions for many different sets of flow rates and analyze statistically using the Kalman filter what we have in pressures compared to what we can predict. And using this algorithm again, so just one iteration is nearly enough. So this is a red line here, practically coinciding with the design this synthetic example showing the true leak distribution inside the system. So once we have this done, so we can know that we leak what amount of gas or oil we leak in each section, and this allows us to determine the approximate diameter of the damage. If we want, we can split each of the segments still shorter segments and determine the location more exactly. So this is just a very simple example, but it shows how this system works in practical applications. There are many other different applications, and I'm talking about oil and gas industry, but they are also applicable in practically in any situation when you have a complex physical phenomenon and technical system characterized by a mathematical model. It can be a chemical reactor, it can be pipeline, it can be aircraft. So these are all different applications. But in oil and gas, it is typical situation is that we can use it for transient property for production fluids, viscosity, density. As I mentioned, the temperature of the system can change, and then viscosity can change. If we have the measurements of pressures, we can adjust our model and evaluate the viscosity at different parts of the system. Variable and non-uniform properties of rock reservoir, and this or it can be not rock, but the environment of the system. Like in different parts of the plant, you have different temperatures of the equipment, and they all can be adjusted using this system, even if you don't have the measurements of the accurate measurements. For example, in the situations when the measurements are very difficult to organize in hazardous environment. The variable geometry of the wellbore. So suppose you have a fluid system, hydraulic system where you have clogging, deposition of sand, for example, or waxing, then the geometry is changing and that the flow rate is changing for the same pressure drop. This can be analyzed using the pressure measurements and the ensemble Kalman filter. Flow regimes are very complex and multi-phase flow. This can be also addressed using the Kalman filter. So these are all sets of problems that can be addressed using the ensemble Kalman filter. And this is a part of the data assimilation algorithm. The data assimilation algorithm is a significant part of machine learning, and machine learning is a significant part of the